Hello, everyone. Uh, this lecture will be about recent topics in HML. It will be a short one, just to shed some light on the recent topics in this area. So I will start with meta learning. So by now we are familiar with federated learning. So in federated learning, there would be a number of agents, and they are trying to learn a global model. And at every iteration, uh, the parameter server will share the current copy of the model with all of the workers or agents. Everyone will perform a local computation step, which could be computing the gradient or performing a local GD step, and then share the updated, either the gradient or the updated model with the global with the parameter server, which performs one global step, could be one SGD step or model averaging. That's the setting of federated learning. Now, if we look into meta learning, in fact, the objective in meta learning is different. The goal here in meta learning is not to learn a global parameter that will be shared across agents. In fact, here the objective is to learn a good initializer. So given a number of tasks, we're going to train an initializer where when a new similar task comes, that initializer will be much better than starting from a random model in order to adapt to the new task. So like this initializer can actually, by this actually we ensure like adaptation to a new task with a limited number of samples. So therefore the learning will be faster and require less number of samples. Now we come to describe some of the recent frameworks that were proposed to solve the problem of meta learning. MAML, which stands for Model Agnostic Meta Learning, is a bi-level optimization-based framework that has been proposed to solve the problem of finding the meta model. The proposed formulation is shown here. The goal is to minimize the average validation loss across tasks, where the validation loss of every task is a function of the validation data set and the local model. And as we can see here, the local model is a function of the training data set and also the meta model. And the relation between the local model and the meta model is shown here in this equation. It's actually the local model. The local model is a KSGD steps from the meta model in the direction of the local problem using the training loss of the of the specific task on its own training data set. So as we can see from this formulation, actually there is double loop, or there is inner problem and outer problem. And in order to solve this, we need to, at every iteration, we need to iterate between the inner level and the outer level, or the inner problem and the outer problem. So, and the inner level, as I just mentioned, the local model is updated by moving KSGD steps from the current meta model. Then after the local models, all of the local models are updated, then we come to the outer level where the meta model is updated according to this equation. It's just one SGD step, where of course, here we need to take the gradient with respect to the meta model, but the meta model is already a function of the local model. Therefore, from the chaining rule, we end up having this formula. So this is the gradient of the local model with respect to the meta model times the gradient of of the local loss for task I with respect to the with respect to its local model. So when we sum over m tasks, then that's actually the like computing the gradient of the original objective function with respect to the meta model. As we can see, this is like the gradient for the I of the local model of the I task with respect to the with respect to the meta model. So as we go more steps each time we update, because again, we are alternating between updating the local models and the meta model. So for every choice of the meta model, we will move, as we can see from this figure, for every choice of the meta model, for every task, we will move KSGD steps. We end up having a new local models. Then these new local models will be used to update the meta model according to this equation, and then that keeps keeps happening again and again until the convergence point. So as we can see here, the goal is that the meta model is the one that minimizes this defined KSGT steps. The average K is like the average loss, such that each local model is this KSGD steps from this meta model. Now, if we, as I said, this is a matrix, and the problem with this now, if you go like number of KSGD steps at each choice of the meta model, the computing the gradient, because now the gradient, for example, the gradient at the for example at the fourth step is a function of the gradient at the third step, which is function of the gradient at the second step, and so on. So therefore, if you want to compute the gradient of the fourth fourth step local model with respect to the meta model, then we need to have like d phi 4 by d phi 3 times d phi 3 by d phi 2 until d phi 1 or d phi 1 time with respect to d phi 0, which is the meta model. So every time, like for example, at the fourth steps, if we have d phi 3 by d theta, then we need to multiply by d phi 4 by d3, and every time, and if this matrix size is large, then because this matrix multiplication has to happen at every step in order to end up having d phi k for task I with respect to theta. So therefore, this matrix multiplication has to happen at every SGD step in order to compute this guy. And that may, because there is no direct relation between d phi k and the meta model, so it has to go through all this trajectory of updates in order to find d phi k by d phi by d theta, and that may, as I said, computationally may be like expensive, and in fact that brings us to the next framework, which is named MAML with implicit gradient. And the idea of MAML with implicit gradient is like, there are two things have been introduced here for the local problem in order to come up with a relationship, with a direct relationship between the model at any step with respect to the meta model. So the first is to introduce this regularization term in the local problem. So when we solve the local problem, when we are finding the local model of task I, we are solving this problem. So we introduce this regularization term, which has explicit relation between phi, the current phi, and theta, and we solve this problem to the end. Therefore, that's why we say alg star here, because every time we're not we solve this problem to the end to find the optimal solution of this problem. And therefore, given that the optimal solution of this problem is the one that drives the gradient to 0, taking the gradient to 0, we end up having like a closed form expression for d phi by d theta. But that, again, there's another problem here. This expression involves matrix inversion, and that's another issue. So for implicit MAML. But now, at every step away from theta, we have like this can be computed using this matrix inversion, and it has already explicit relation between the current phi and theta. So there's no need for this involving chaining rule in order to compute the gradient. Also, the paper has introduced an efficient algorithm. The paper that proposed this framework, which is, by the way, here in this reference. So here you can, if you are interested, you can, in the details, you can read through this paper. So this paper has introduced an efficient algorithm to approximate the matrix inversion. So they do not really do matrix inversion at every step, but they approximate the solution of that to to reduce the complexity of the algorithm further. Now we come to the topic of federated meta-learning. And in fact, for this topic, I will include about like 15 minutes or so from my presentation for GlobeCom 2021, where I recorded a presentation that actually describes the notion of federated meta-learning and also describes our proposed framework. I will include the part that describes the theory and the framework, but if you are interested into more details on the topic, including the results, you can actually watch the whole video on our channel on YouTube, Icon channel. After those 15 minutes, we will go to the again for both of these works. The inner and outer problems are there, and like in order to solve the problem, we need to iterate between the inner and the outer problems. Therefore, in this paper, we propose a more efficient way to solve the problem of meta-learning. We can see in this figure, we assume a distributed setting where every task is owned by different agent. And we also assume like we have like at each agent, a model is trained for that specific task. So we start from the optimal models of the different tasks, and we, using projected gradient ascent, we propagate towards a unique initializer. So the idea is to run gradient ascent and project the output into a feasible set that is minimized at every iteration until we reach a unique model that's going to be the meta model. With this approach, we actually avoid double looping, and we also avoid matrix inversion, and we can solve the problem very efficiently. Now we describe our formulation for the federated meta-learning problem. We start by with this optimization problem. The objective is to minimize the sum or the average of the square difference between the loss at the meta model and the loss at the local epsilon optimal model for task I. So we sum over all tasks and we divide by the number of tasks. So we compute the average distance, and we introduce this constraint here, and this constraint simply says the local epsilon model, the local optimal epsilon model for task I is ki SGD steps from the meta model. This is very similar to the formulation of the MAML. Therefore, it's actually as hard as, like solving this problem is as hard as solving the original MAML problem. Therefore, we consider this relaxation. We introduce here some of our case tips. The idea at high level is that we are finding a trajectory of points, k points, where like where every point, where we are minimizing actually the distance between every point and the next one. And actually the next point is one SGD step from the previous point. It's actually not really exactly SGD, because the gradient here, not with respect to the starting point, but to the with respect to the ending point. And under like a smoothness assumption, the error or the difference between these two gradients is not big. But this will significantly simplify the way we solve the problem, because actually our algorithm is a backward algorithm, starting from the last k point and going back to the 0th point. So this is the objective function, and we introduce this constraint. This constraint simply states that for task I, the model at iteration k, or the kth point in the trajectory, the model there is the distance between that model and the average model is less than or equal some delta k. And at the for the when k is equal to 0, this has to go to this has to be 0, because they all meet at that point, the initial point. Or if we look from backward, it's the last point. And we initialize the model from backward, which is the last point. Actually, if we look from forward, we initialize the model of every of our algorithm to the optimal epsilon model of every task. So now this formulation or this problem is much easier to solve. It's a good approximation of the original one, and here is the way we solve it. So at backward step k, we need to solve this problem. Again, we started, as I said here, we started, this point is already known. So phi I k capital is already known. So then we start from there, and we move in a backward manner, and at backward step k, we solve this problem. One thing I forgot to mention in the previous slide, as we are moving backward towards the 0th point, delta k is actually a decreasing sequence. So we are moving backward, and we are shrinking the physical set of our solution. Now this problem can be rewritten this way. We just rewrite this constraint this way. We just like define this as a physical set, and phi I has to belong to that physical set. And this the set is the like any phi that satisfy this constraint is belong to the physical set chi I. With that, we actually can rewrite it as a unconstrained optimization problem, where we introduce this indicator variable, and this simply states that phi I, if phi I belongs to chi I, then this indicator variable is equal to 0 and infinity otherwise. So this is like just another way, unconstrained way of formulating the problem. Now this problem is easy to solve. In fact, it involves only 2 steps. And here are the 2 steps. The first step is gradient ascent step. And in fact, if we look into this problem, we will find like, since this is always a positive quantity that is greater than or equal to 0, then if we ignore the indicator variable, then the optimal solution of this problem, because we're solving with respect to phi, the optimal solution is when phi is equal to this, which is what we have here. And that's the first step. We come up with the initial solution. So if that solution is in the feasible set, then we're done. That's it. That's the solution. The minimizer of this is exactly this point. If this doesn't belong to the feasible set, then we do projection, orthogonal projection, and projection is just solving this optimization problem, which actually can be solved in a closed form expression, and the details of solving this problem has been described in the paper. Now I come to another interesting topic that has been recently investigated. Before I jump into the details of the topic, I need to revisit uh, the setting of federated learning. There is in federated learning there is a parameter server and number of workers. And when the system is a distributed system with wireless network, usually the assumption is that the underlying communication system is a digital communication system where every element, where like at each iteration, the workers need to upload the gradient or the local model, and every element in the uploaded vector is encoded using B bits. Therefore, like each worker needs to transmit B times the size of the model bits, and if this like the number the energy and the power needed to transmit to like ensure successful decoding of the bits at the server depends on the channel. And also there is a competition on the available bandwidth or available channels across workers. So as we accommodate more workers, there will be higher competition on the available communication resources, and the communication resources will be the bottleneck. Therefore, uh, people have thought about like more scalable solution exploiting the structure of the learning problem, because learning problem is actually a unique problem that has its own structure and its own features. And if we exploit them, we may consider more communication efficient and scalable communication system. And that was like the driving reason to go from assuming digital underlying communication system to designing analog over air system to involve analog system and to introduce analog over air aggregation scheme to enable scalable federated learning. And the actually motivated by the fact that the parameter server is not interested in decoding the individual element for every worker. Rather, it's actually interested in the aggregated value of all these workers. This system has been proposed. So we don't, the parameter server doesn't really need to decode the individual output of every worker. So if we can aggregate the outputs of all workers, then this is all we need at the parameter server in order to update the global model. Therefore, in the training uh, job, we are not really, we don't really need to decode the individual element of every worker. If we can send that element and with the help of the air, so we get all the elements of all workers get aggregated in the same time slot or over the same subcarrier, then actually the air is doing the job for us. And then the parameter server doesn't need to do a complicated digital decoding algorithm in order to decode the individual outputs of all workers. And workers do not really need to compete in the communication resources. So the ith element of every worker can be transmitted on the same time slot or over the same subcarrier. And therefore, if we can accommodate more workers, because actually the bandwidth, uh, like uh, uh, like the bandwidth or the time slots are not function that are needed to transmit the elements of all workers are not function of the number of workers anymore. It's function of the actually the model size itself. So as we with this we can accommodate more and more workers, and it's scalable in that sense. But one thing I want to mention about the standard way of implementing analog, in order for the parameter server to receive the ith element uh, of every worker at the ith channel, every worker needs to perform channel inversion before transmitting. And that channel inversion has its own limitation as well, because now the channel could be a very low. For example, if a worker has like channel equal to 0, then that worker cannot transmit at that time. And actually, we need to specify a certain threshold. And if the channel is higher than that threshold, then this element will be transmitted from this worker. If it's not, then that element doesn't need to be transmitted. And that needs more information about who, like for per element, which node, like how many nodes are transmitting, and also the choice of that threshold. Like because as I said, we are defining a certain threshold. If the channel in that like if the channel gain on that subcarrier for a specific user is less than this threshold, then that user cannot transmit that element. So the choice of the threshold itself is critical and also affects the convergence guarantees. And therefore, we actually introduced another framework. So this is our contribution uh, to federated learning with analog and over-air aggregation, where we integrated the channel into the optimization problem or in the federated learning problem. And we actually show that we don't need to specify threshold. And in fact, by introducing this channel into the problem, we don't need to perform channel inversion at the transmitter, because we are actually solving a little bit different problem where the channel is integrated into the problem. And it's becoming a co-design of communication system and federated learning. Now I come to describe analog federated learning into more details. I'm talking about this one, the one in the middle. So I start by writing the received signal. So y n of t is the received signal at time slot n of iteration t, which is the aggregation of the individual received signals. So where like xmn of t is the transmitted signal from worker m at iteration at time slot n of iteration t, scaled by this is element-wise multiplication. So every element in X is scaled by the corresponding channel. And we introduce this indicator variable here, which is equal to 1 if the user M is transmitting on time slot N at iteration T and 0 otherwise. And we have the additive convex Gaussian noise. The transmitted signal is actually the gradient vector, where every element is scaled by the scaling factor alpha, which has to be chosen such that the power constraint at user M is satisfied or it's not violated. And this gradient vector, actually, for every subcarrier, we utilize both the real and imaginary components. So every subcarrier can actually transmit two gradient components. So this gradient is the aggregation of all like real and imaginary. So it's the concatenation of all time slots, where every time slot we also have like all the carriers, the real channels first, and then the imaginary comes after. So this is the vector of the transmitted gradients, or the gradient vector that is transmitted from user M at iteration T. So as I said, alpha has to satisfy the power constraint, and also alpha includes the channel inversion process on it. So alpha is some gamma over H. In fact, alpha is some gamma over H if this condition is satisfied, if the magnitude square or the power on the channel is exceeding a certain predefined threshold, then gamma is greater than 0 and it's equal to this value. Otherwise, gamma is equal to 0, and that specific worker M, is not transmitting on subcarrier I at iteration at time slot n of iteration t. So here M is the mth worker, I is the ith subcarrier, and n is the n time slot at iteration t. Again, as I mentioned, alpha has to has to be chosen such that the power constraint is not violated. Therefore, we need to solve this optimization problem in order to find the value of alpha. And I'm not gonna go into the details of solving this problem. The details are explained in this paper. But just to mention, like alpha has to be chosen according to by solving this problem. Here, the average power is actually 1 over the number of time slots times the number of iterations, where we sum over the number of iterations and number of time slots per iteration. We sum the power, and that average power should be less than or equal to a predefined threshold. So now I come to write the received signal per subcarrier. So for the received signal on the subcarrier I at time slot n of iteration t is actually the aggregation of the individual signals on that subcarrier. We have real and imaginary channels. So the gradient, so every worker is sending one component on the real part and another one in the imaginary part, and those ones are sent from different users on the real part of the subcarrier are aggregated all together over the air, and what reaches the parameter server is the aggregation of those values. So here we sum over m belong to the set. The set contains the set of workers that are transmitting on subcarrier I at iteration n. So then if this is the received signal, then the parameter server, the only thing that needs to do is just to divide by this quantity. So take the real channel and divide by this quality, and here the same thing for the imaginary channel. So for the real and the imaginary, we divide by this quantity, and this quantity is just the average gamma, which is actually, because now every individual worker has different gamma. So ideally, everyone has to be because now when we are dividing by average gamma, we're not really constructing the exact gradient of everyone, because we're not dividing by this gamma, because the gradient was scaled by this gamma. Because now the transmitted signal is what? Is the gradient times gamma over h, and that will be scaled by h. H will cancel with h, then we will have the gradient times gamma m. So when we are dividing by gamma average, we're not really reconstructing the gradient, the sum of the gradients, because this is, again, the real yi is aggregated gradients of different works. So we're not really reconstructing the sum of the gradients, because again, this gamma is different from the scaling factor. It's actually different across workers, but the average one will still give us a good estimate according to the paper. There are, I think, under some assumptions and constraints, this value is still a good estimate of the exact gradient. So okay, so then again, coming back to this, we divide by this quantity, which is the average gamma, times this quantity, which is the number of workers that are transmitting on subcarrier I at time slot n of iteration t. So by if this set, if this number, if this set is not empty and this number doesn't equal to 0, then we divide by this quantity and we reconstruct the estimate of the gradient. Otherwise, the estimate of the gradient on the real channel of subcarrier I is equal to 0. Same thing for the imaginary part. And with that, we receive some of the gradients or aggregated gradient in every subcarrier, which is aggregated of value of one element across workers. Yeah. One thing before I go to the next slide, I kept saying like we receive the aggregated gradient or the sum of the gradients, but just to be mathematically precise in what I'm saying, we are not really receiving the sum of the gradients, because gradients, a gradient component that are received from different workers are scaled differently, because gamma is different across workers. So we are actually receiving weighted sum of those gradients. And when we divide by the average gamma, we reconstruct the estimate of the sum of the gradients, which is not really exactly the sum of the gradients. Now I come to our approach. Our approach is a little bit different. So we do not involve channel inversion. In fact, we are solving this problem here, where we introduce the channel in the constraint. And in fact, the channel is added to both sides, right and left sides. So it's not really affecting the solution of the original problem. And by reformulating the problem into this constraint optimization problem, then we actually can write the augmented Lagrangian of ADMM. And after writing the augmented Lagrangian of ADMM, then we end up having the the update of the. So here we have local models and we have global model. So at every iteration, all the workers will update their local models by finding by solving this problem. By now we should be familiar with ADMM. So given the Kate version of the global model and the Kate version of the dual variable, we update the local models at each worker by solving this equation. And then all the local models are transmitted to the parameter server. And actually not the models transmitted. So what we are transmitting is this, where is it here? Let me check here. So this is uplink. So what we are transmitting from each worker is H conjugate times theta plus lambda over rho. So when we transmit that value, it will get scaled by H, and then we will end up having at the receiving side, we will end up having this. Feeding this through a matched filter will increase the signal to noise ratio, because the noise is random with zero mean, and the signal is constant over this integration period. So we end up having this is just like, as I said, it's just like increasing the signal to noise ratio. Then the output will be this, and this is exactly like this plus the noise is exactly a noisy version of what the parameter server needs in order to update the global model. So that's used here. Of course, we divide by this here. That is as a result. It comes naturally when we write the updating equation according to ADMM for the formulated problem, but the sum of H square can be estimated because we are not estimating the individual channels, we are estimating the sum of the sum square of the sum of the square channels. So that is one pilot signal transmission from the workers, because again, if you think of how the channel estimation is happening, actually the parameter server will send one pilot signal in the DAO link, and every worker can update the individual channel, and that when every worker estimates the individual channel, and under the assumption of uplink downlink symmetry, then every worker can send H conjugate, which will be received because H conjugate times H will be H square, and the parameter server will be able to estimate the sum of H squares. So the parameter server doesn't really need to estimate the individual channel, which can come at very high cost in terms of the using the resources. But the good thing about this framework is that the parameter server doesn't really need to estimate the individual channels. It's enough to estimate the sum of the estimate this term. And as I explained it, estimating this can happen at low cost. It's just every channel coherence time, the parameter server will send one pilot signal, and every worker can estimate the downlink channel. And under the assumption of downlink uplink symmetry, every worker sends H conjugate, then this guy can estimate this value. and that this will happen once every coherence time period. So then the updated model is updated according to this equation, and then it's downloaded by all of the workers. So if we assume even like if we assume like the downlink is also utilizing analog transmission, then the same process happening at the uplink. But of course, we don't. So what we receive is actually h theta. So then every worker can just feed through matched filter and then can use this value to update its local model. But again, for the downlink, we don't really need to utilize analog communication because there is no competition on the available communication resources on the available bandwidth, because it's just one node is transmitting to every node. So digital scheme can be utilized for the downlink, but analog scheme for the uplink. Here, yeah, the figure is actually explaining here, like here is the transmitted signal from from each worker at iteration t, and here is the process, like as I explained it at the parameter server, and then every worker in the downlink will receive the signal because the parameter server is sending theta, so every worker will receive h theta plus c and feed it through a matched filter to increase the signal to noise ratio, and then scale by h conjugate, because every worker is easy to estimate the channel at the worker side. So every worker knows H conjugate. So by scaling the output of the matched filter with H conjugate, we end up having this quantity, and this quantity is exactly this one. So we can solve this problem very easily, and we can implement uplink, and we can implement analog in uplink and downlink. Then the dual variables are updated according to this equation at the worker side, and it's the workers have all the information they need to update the dual variables. That's like this at very high level, like how this scheme is working. Again, it doesn't involve channel inversion or a decision or a predefined threshold on which one to transmit at every iteration. So all the workers are transmitting at every iteration, and if the channel is zero, then the signal will die by itself. It will not reach the parameter server, and that's fine, since the channel is already integrated into the problem. So more details about this scheme and how we do, because I explained it here now, I didn't go into the details of power constraints and how we work with this power constraint issue. So more details on this approach are explained in this paper. So you can go and read through this paper, and if you have any questions, I would be happy to answer and help. I think with that, I come to the end of this part. I would like to thank you all for watching the videos and enrolling in the course. And if you have any questions or if you need to go deeper on any of these topics, I will always be available to help. Thank you.